Alright, here we're going to take a look at quiz number 2 from 2016, Unit 2. The key for this. First question here is asking us, what happens to a molecule when hit with IR waves? What does IR tell us about a molecule? Alright, so what does IR tell us about a molecule? What happens in IR? Bonds in a molecule stretch and bend from the infrared radiation that it hits it. And IR tells us about function groups that are present. Two big things. Number 2, to draw the molecule in the brackets that gave the two fragments below. So you're given the two fragments below, the positive fragment and the neutral radical. And I'm asking you to work backwards to say, where did these two things come from? So you need to number these carbons. That's probably the most important thing here, is to number these carbons. So 1, 2, 3, 4, 5, 6, 7. And according to this, where the carbocation, the plus charge carbon, and the radical, that's where the bond was at. That's the bond, what it was. So you need to draw that bond between 2 and 6 in this case. There's your actual product. The thing we actually detect is the positively charged fragment, and what this is called in the brackets is called the molecular ion, just minus 1 electron. That's the molecular ion. So for number 3, first part, draw the molecular ion for the molecule below, including all electrons and charges. So the first step, what happens is when an electron gets ejected from this chlorine, right? So one electron gets ejected by the electron beam. So once the electron is ejected, you get the molecular ion. And what I'm asking you to do here then is saying, here's one alpha cleavage, right? So there's 2 alpha carbons in this molecule on either side of the functional group. So 2 alpha carbons, right? I'm showing you one alpha cleavage, and I want to see the other one, the mechanism for the other one. So an alpha cleavage is a homolytic cleavage, meaning fishhook arrows, one electron moving at a time. So the first one, the electron from the chlorine goes to here. The electron from this bond between the carbon and the chlorine and the alpha carbon breaks. One of those electrons goes there to form that new pi bond. And the other radical, the other electron, goes to the other alpha carbon to give a CH3 radical. So the neutral radical, make sure you draw it as a CH3. Once you only have one carbon, you have a CH3. A lot of people try to draw it like this, but this is representing 2 carbons, so you got to draw a CH3 dot. And the positive fragment is actually the fragment with the chlorine in it. Be very careful with these arrows. Learn how to use these arrows, these heterolytic cleavages, or this homolytic cleavage, alpha cleavage. You know how to do alpha cleavages with chlorines, the alkyl halides with alcohols, ketones, and ethers. So number 4, just asking you to label 3 important IR peaks. A lot of people have labeled more than 3, just 3 is enough. So here's the ones I would have looked for. sp2CHs past 3000 from the aromatic CHs, right, from the aromatic ring. sp3CHs from over here, this methyl, which would be below 3000. The CC alkyne stretch, the CO stretch from the ketone, and then the 2 peaks that represent the CC double bonds, pi bonds in the ring. But in the aromatic ring, you have to have 2 peaks, not just the one. It has 2 peaks. So any 3 of those would be acceptable. Usually don't try to do more than 3, just do the 3 you need. Number 5, would you expect the CO stretch in the molecule below to be higher or lower than a ketone stretch? So ketone stretch is at 1710. So we'd expect that to be different here because this fluorine is very electronegative, so it's going to pull electron density. It has nothing to do with the mass. It's just pulling electron density, so we expect it to be higher. It's going to shrink and shorten that CO double bond. And once that's shorter, right, because F is very electronegative, will inductively pull electron density, shortening the CO double bond, making it stretch at a higher frequency, because it's shorter, it's going to stretch much faster and at a higher frequency. It's all about induction in this case. Fluorine does have lone pairs, and resonance is possible, but it's just not as likely. Induction is much more likely. Fluorine is very electronegative. Same kind of question below here for 6. Which molecule CO, carbonyl below would you predict to stretch at a lower wave number or lower frequency in IR spectrum NY, and you must use drawings. So what I'm looking for here here's an ester, here's an amide. The only difference between these is an oxygen versus a nitrogen. So what's the difference between oxygen and nitrogen? Well, oxygen is more electronegative. So it's going to be about induction for an ester. It's going to pull away electron density. Whereas the nitrogen, because it's less electronegative, it's more likely to do a resonance structure. Right? This oxygen is going to be very similar to this fluorine. It's going to pull away. It's going to have a higher wave number because it's shortening this CO double bond stretch. The amide is going to be the one that's actually lower. Because of this resonance, you have some single bond character. Right? Make sure you can draw resonance structures. You have some single bond character here, which is going to be a longer bond, which would mean it's going to go at a lower wave number and at a lower frequency because of this resonance form. For number 7, rank the molecules below from shortest unwanted number 1 to longest wavelength 3 UV absorption. Here you're just looking for conjugation with pi bonds or lone pairs. So this one has 1, 2, 3, 4 things in a pi system. So I would have the longest wavelength, the most conjugation. 2 would have 1, 2, 3, and then 1 here has 1, 2. So it would be 3 of the longest, 2, 1, more conjugation, longer wavelength. Don't forget lone pairs can be part of the conjugated system. Lone pairs and pi bond electrons. For the bonus here, basic ring flip, we have an axial up CH3. So when we do a ring flip, we should have an equatorial up, right? If you're up, you're always up. But if you do a ring flip, you go from axial to equatorial. The number of non-equivalent hydrogens, because this ring flip can happen very fast, essentially the 2 hydrogens on 6 are the same, and they're the same as the ones on 2. This molecule is very symmetrical. So as I had drawn over there, this molecule is very symmetrical, so you can see symmetry. So if I zoom in on this, the non-equivalent hydrogens, obviously the CH3, those, H right there, C's, B's, and A, so it's 5 non-equivalent hydrogens.